Happy Monday, section 9.2.2. How can I use inequalities or solving inequalities? So we're going to pick right back up with inequality stuff this week. And the last lesson you learned how to solve inequalities with one variable. Today you're going to focus on special inequalities and learn how you can use inequalities to solve an application problem, otherwise known as a word problem. Okay, so we're going to do the first two problems together, A and B, and then we'll get the music going. We're going to jam out, and I'll do these ones. I'll have the answers up here, and you're going to do them on your own. Do them on your own, and then you're going to check your answers and go through your process and make sure that you're following the steps and you're working everything out and you're fixing your errors, okay? First two, and then we'll get that music going, and you'll be on like Donkey Kong. Question 956, review what you learned in lesson 9.2.1 to solve the inequalities below. Represent your solutions both as an inequality and on a number line. So we need to get a final inequality that's more simplified this and also get a number line. So two things required in a question like this. This here is a pretty simple looking inequality, but we don't have the variable isolated. So the final answer should have a variable isolated, right? It should clearly state what the variable needs to be in order to make this inequality statement, x minus 7 is less than negative 2, true. This one we'll also do together. When you find the values of m, that you take that m and multiply it by 3 and add by 2, and it would still be less than or equal to 8 times that m minus 8. And we'll do those together, you'll do the rest together. And then can't forget that number line, part 2. First thing, step 1 in these guys here is we need to solve for our boundary. So remember, the boundary on the number line is going to either be the lowest or the highest value that the inequality, the variable is allowed to be to satisfy the inequality. So there could be one boundary, there could be two on some of these, and we'll see in a second. So we'll solve for our boundary. So in order to do that, we're going to change this to an equation. Because that point that the left side actually equals the right side is going to show us where our inequality will begin or where it'll end, or where it will be pretty close to the beginning or pretty close to the end, which we'll see in a second. So changing it to an equation, let's solve for our boundary. I'm going to add 7 to both sides, and I get x equals 5. Okay, there's my solution to the boundary, but is that our solution to the inequality? No, it's not an inequality. So step 2 is test a point. And what that really means is just one value for x, because again, our final solution here, our number line solution, is going to be a one variable number line. So it's going to have x here, and it's going to get bigger, it's going to get smaller this direction, and we just need to test a point on either direction. So we have a boundary at 5. I'll go up to 1, 2, 3, 4, 5, and that will be a boundary point. One thing that I'm going to check here, okay, so this is a less than symbol right here. So because of this, I'm going to have an open circle. Make sure you write that in your notes. Less than symbol gets the open circle. So that'll be an open boundary at 5. So now I need to figure out, my solution is going to be the values bigger than 5, or are they going to be less than 5? So if I'm going to test a point, I'm probably going to test this point right here. Let's test this one. I'm going to test x equals 0 in the original inequality to see if 0 is a solution. So let's check it out. So I'm going to try 0. And I'm going to get 0 minus 7 less than negative 2. And I'm going to see very quickly, because I plug in 0 here, I can even just cross 0 out and I get negative 7 less than negative 2. And that's certainly true. It is less than negative 2. So we know that 0 is a solution. So that would be filled in on our number line. And this is going to tell us, because 0 is a solution, we have only one boundary right here. Anything that's on the same side as 0 is going to be a solution, because if one point on the side of the boundary is true, then all other points would be true for that inequality. And we can write our final answer right down below here. So final answer is going to be x needs to be less than 5. There's our final answer. Did we do both things we needed to accomplish here? And inequality is our final answer? Yes, x is less than 5. And get a number line. Yeah, we got this one here. And so we're good to go. Okay, part B. Let's do part B together. Step 1, solve for boundary point. 3m plus 2 is going to equal 8m minus 4. That point of equality is going to be where the inequality either begins or ends in the final answer. So what I'm going to do is I'm going to collect my m's to this side. So you always want to take your variables, you want to move them to the side where there are more variables. No reason to move them to the side where there are less variables, because then there would be a negative variable number here. So I'm going to move my m's over here, and I'm going to move my 1's over here. My constant terms are going to go over here. So I'm going to add 8 to both sides, plus 8, and I'm going to subtract 3m from both sides. So I've eliminated this over here on the left side, and I've moved a negative 3m to the right side to make an equivalent move. And I've added an 8 over here to eliminate the negative 8. And then I've raised this up by 8 as well. I've added 8 to the side to make sure that the equality statement at the beginning got fulfilled. So now I have 5m equal to 10. So my boundary point is going to be at 2, because 10 divided by 5 is 2. And that's my boundary. Step 2, we're going to test, you guessed it, 0. And I'll do that in the original inequality. So I have here 3 times by, I'm going to plug in 0 twice, 0, plus 2 is less than or equal to 8 times by 0 minus 8. And my zeros cancel out with the coefficients in front that are multiplying to that 0. And I got 2 is less than or equal to negative 8, and that's a false statement. So it's false here. So in my answer, what I'm going to get here, and again, you don't have a ton of space, I'm going to have to add more space on this here. This is false. This was true over here. So if it was true, then 0 is a solution to this first one, and everything on this side of from the 5 that where 0 is located is a solution. If it's false, and let's draw out our number line here for part B, we have a boundary point at 2, and because this is less than or equal to, it's okay. The boundary is going to be part of the solution. It's an inclusive inequality. It's going to include the boundary. And we tested 0. It was not a solution, so that means we need to shade the other way. We need to shade to the right. So you test 0. 0 is just the easiest point to test. You test it. If it's true, then you shade the direction of 0 on the number line. If it's not true, you shade the other way. You shade bigger. I think we need one more example. Oh, I forgot the most important thing is that I forgot to write my answer as an inequality at the end. So my last thing is going to be writing that x needs to be greater than or equal to 2. Can't forget the or equal to because it's inclusive. X is allowed to be 2, and if I tested my answers here, right, if I plugged in 2 here, I would get 6, and then it would become 8 because I'd add 2 to it. And then here just be 16 minus 8, which is 8. And then if I tested another solution, because remember there are infinitely many solutions that could work in this inequality. If I tested 3, for instance, I would get 9 here plus 2 is 11, and that's less than or equal to 24 minus 8, which is 16, right? 11 is less than or equal to 16. 3 is the solution. We know we're good to go. So you can kind of quickly get the answer in your head as well. Let's do this one. Let's get our boundary point. I'm going to write a little bit less here so that we can see our answer a little bit more clearly. So again, switch to an equation. Get that boundary point. So I'm going to add 2 to both sides. So when you solve, you do reverse PEMDAS. So 2/3 is being multiplied to p, and then negative 2, and then we have a subtraction of negative 2. So this negative 2 is further away from p, right? It's something we would do kind of last in PEMDAS. We'd have to multiply first, and then we'd have to subtract afterwards. So do reverse PEMDAS when you're solving. So we need to get rid of the subtraction here. So let's add 2 to both sides, and we would get 2/3 p is equal to negative 2. And then you have to remember what you have to do in order to solve for 1p right here. The trick is when we have a fractional coefficient, when you have a fraction in front, the way to get rid of it is you multiply by the reciprocal. So that's this 3/2 thing. So if you multiply 2/3 p multiplied by 3/2, then you would get your numerators multiply together. That's the rule with fraction multiplication. 3 times 2 is 6, and denominators multiply together. 2 times 3 is also 6. So then you'd have 6/6, which would just be 1. It would just be 1p. You remember, in order to keep an equation balance, right, a statement of equality balance, if you do one thing to one side, you have to do the same thing to the other side. So I would also have to multiply this side by 3 over 2. And on this side, I would get negative 2 times 3 is negative 6 divided by 2. So negative 6 divided by 2 is negative 3. And that is my boundary point. P equals negative 3. So I'm going to go ahead and draw in my number line. And negative 3 is the thing that I really care about. I have a negative 4 there, but I don't really care about that because I have an open circle at negative 3. And I just need to figure out what direction to shade. So again, I'm going to test 0. And I'll put that into my original inequality, which is going to be 2/3 times by 0 minus 2 is greater than negative 4. And here, if you're really quick, you can do this in your head. 2/3 times 0 is just 0. Get a 0 product there because we had a 0 factor. And then is this statement true? Is negative 2 greater than negative 4? Well, yeah, negative 4 here is lower on the number line. Negative 2 is greater than 4. So that statement here, we tested 0 as a potential solution, and it was true. So that means we can shade the side of 0. Did we have to test 0 there? Was 0 the point that we needed to test in order to determine if this is the way to shade? No, we could have tested 1, we could have tested 2, we could have tested 3. But if you tested all of those, they would all be true, right? They would all be true. So you can test any point on either side of the boundary point to see if that side is a solution or not. Okay, I think that was enough of a warm-up. We'll write our final answer here too. X is greater than negative 3. So what you're going to do now, let's get some jams going. And you guys are going to try out D, E, and F right now. And we'll come back together in a minute or so to review our answers. Ready, set, go.
They say, oh my God, I see the way you shine. Take your hand, my dear, and place them both in mine. You know you stopped me dead while I was passing by. And now I beg to see you dance just one more time. Ooh, I see you every time. And oh my, I like your style. You make me wanna cry. And now I beg to see you dance just one more time. So they say, dance for me, dance for me, dance for me, oh, oh. I never seen anybody do the things you do before. They say, move for me, move for me, move for me, eh, eh. And when you're done, I'll make you do it all again. I said, oh my God, I see you walking by. Take my hands, my dear, and look me in my eyes. Just like a monkey, I've been dancing my whole life. But you just beg to see me dance just one more time. Ooh, I see you every time. And oh my, I like your style. You make me wanna cry. And now I beg to see you dance just one more time. So they say, dance for me, dance for me, dance for me, oh, oh. I never seen anybody do the things you do before. They say, move for me, move for me, move for me, eh, eh. And when you're done, I'll make you do it all again. They say, dance for me, dance for me, dance for me, oh, 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 oh. I never seen anybody do the things you do before. They say, move for me, move for me, move for me, eh, eh. And when you're done, I'll make you do it all again. Ooh.
Did you get these ones? Well, E and F were kind of curveballs to you. You might have had to stop and kind of thought about those ones. So maybe you're watching these being like, well, am I interpreting this correctly? Check it out. Are you interpreting this one? Are you interpreting this one correctly? And this one you're just checking. I know in these problems, these could seem very easy, and there are other ways to do them. Just this, if you're following the logic here, you're doing the logic here, I think you're going to make fewer mistakes. But it can be easy to forget everything because, again, you need to have a final answer that's written as an inequality, a variable being isolated next to an inequality symbol, and just showing you what the solutions of that more complex inequality would be. And here x would have to be less than or equal to 5 to satisfy that original inequality or our given problem. And because this started with a greater than or equal to symbol, you do shade it in here, right? You shade in this boundary point because if x were 5 here, and you can quickly kind of do it in your head, it would be a solution because 2 minus, well, that would be 15 minus, plus 3 would be negative 12, would equal and that's why we check our answers. Okay, so I just fixed this because I noticed I made an error here. When I was solving for my boundary point, I missed that this was negative 3 was on the outside of parentheses. So this needs to distribute in. Okay, so let's check if I got this one correctly. I'm quickly check this in my head. Is 3 a solution to this inequality? Well, let's check it out here. 2 minus 3 times 3 is, so we're subtracting 9 here, so that would give us down to negative 7. And then we got to add 3 to that because negative 3 times negative 1 is positive 3. So that's negative 4 on the left side, and 3 minus 7 is negative 4 on the right side. And negative 4 would be greater than or equal to negative 4 because the left side's allowed to be either greater than or it can be equal to the right side. So the point of equality, which is the boundary point, is a solution in this problem. So 0, the one that I tested, is still a solution to this one. So if I plugged in 0, I would have 5 on the left. 2 plus 3 is 5, and I would have negative 7 on the right side. So 5 is greater than negative 7, and the rest is history. We got this done out correctly here. These ones were a little bit complicated. So these ones, when you simplified it down, solving for the boundary point, you got to something which you're used to. If you have an equation and you have one side equal to the other side, then that means anything you plug in for k would be a point of equality on the left side to the right side. And is equality actually allowed in this inequality problem here? Well, yes, this has an inequality symbol, right? Less than or equal to. So it's kind of a combination of an equation and an inequality. So if the left side is the same exact thing as the right side, then any value is going to satisfy this inequality. We plug in 100 here, and the left side is going to equal the same thing as the right side, and that's allowed. So on your number line, a little bit tricky. This is where you're putting in your notes. Well, what if I have all real numbers as solutions to my boundary points? Then any real number is technically going to be your boundary point. So you could plug in anything here. So you might as well shade in the entire real number line to reflect the fact that all real numbers can be solutions. This one is different. If you notice this one here with the same thing on the left and the same thing on the right, are they allowed to be the same in this particular inequality? No. Right? This would be a series of an infinite amount of open circles on our number line. So there are no solutions that's going to make the left side less than the right side because they're always going to equal each other. There are identical expressions on the left and the right. So there are no solutions to that inequality, and that's what your number line looks like. It's just a number line not filled in at all. Always get good questions about those ones in class, so it's kind of too bad we didn't do those where you can check your answers and whatnot. Hopefully I got the top ones correct, so I'm not going to check my answers. Email me if you see that I made a mistake, and that would be helpful. So let's go into this. Here's our application problem today. The United Nations. So we're big on the United Nations in this chapter. United Nations deals with a lot of inequalities, right? There's a lot of inequality in the world. There's a lot of different wealth gaps that exist in different countries, and the UN kind of organizes countries and what they're capable of, and so if certain countries have a certain amount of capacity or are able to do certain things at certain amounts, they'll want to know that and compare it to one another. So inequality problems work great for world decision making and world government problem. You're always dealing with inequalities in the world, so might as well take one of the biggest organizations governing the world into consideration here. So at the end of the chapter, your team will have the exciting responsibility of representing a country at a special meeting of the United Nations. So very nice. The UN needs your help in preparing for future large-scale disasters. You will need to help find a solution that not only works best for the country you represent, but that also accommodates the needs of each of the other countries. To prepare for this task, the next several lessons will present daily problems to familiarize you with the important issues and concerns of other countries. Start by writing and solving an equation or system of equations that represents the problem below. Be sure to identify any variables you use. Turkey has a population of 66 million people and is made up almost entirely of two groups, ethnic groups, Turks and Kurds. There are 4 times more Turks than Kurds. Write an equation and solve it to find how many Kurds live in Turkey. So the big problem, this is all just kind of background of what you're going to do the next few lessons. This is where the problem is. We need to start by writing and solving an equation or system of equations. So we're going to have equal sign here. We're not going to have inequality symbol. So I'm just writing down what we need to do. It's good to take notes. Like, this is what I'm going to have to do. And then here's the information to allow me to do that, what it's describing here. So we need to represent the problem below. Be sure to define any variables that you use. One thing that I never really told you, which could be helpful for you when you have to define variables, is actually starting at the end of the problem. So look at end of problem. And this is helpful because the end of the problem, it usually tells you what you're looking to solve for or finding out. And if you can define a variable based on what you're trying to figure out, then that might be easier to then come up with the equation or equations earlier for it. Okay, so let's look at this as an example here. What we're trying to do in this problem is we're writing an equation to solve it to find out how many Kurds live in Turkey. So ultimately, we'll have to solve for a variable. Representing what? Right, representing what? Well, how many Kurds live in Turkey? So let's have that be the variable we're defining. So remember, with defining a variable, we need to write a let statement. And our let statement here is going to be let k equal the number of Kurds living in Turkey. And I include number there, and that's important because anytime you define a variable, you need to include units. How is it being counted? Well, this is just a pure count. There are no specific units of measurement. We're just counting the number of people. So number of Kurds living in Turkey, that's our variable. Let's see if there are other variables here. So remember, this is ultimately a variable we're hoping to solve for, but there might be other variables that we need to compare k to. So Turkey has a population of 66 million people, and it's made up almost entirely of 2 ethnic groups. Okay, so it looks like we defined K so far for Kurds, number of Kurds living in Turkey. Looks like we need to define T equals number of Turks, the ethnic group Turks living in Turkey. Makes sense, Turks living in Turkey. I see that. So it looks like we have a one statement right here. In addition to, we got to use a 66 million number at some point. So remember when we did systems early in the year, usually there's a total quantity equation, and that actually we can define right now. So let's get our total quantity equation right here. So we have K plus T, right? The total amount here of Kurds plus the Turks is about 66 million. So equals 66. And I might do this. I might do number of Kurds living in Turkey in millions. So I'm actually going to define that, how this is measured. It's going to be measured in millions. And that's going to allow me to set up my first equation with just a 66 there. K plus T equals 66, rather than just having all these zeros. So that's the beginning of my problem. I know it says it's almost entirely Turks and Kurds, so just make it simple, make it elegant, just put an equal symbol there for 66. Sure, there are probably a few other ethnic groups there, but what the problem is hand-feeding us is K plus T is equaling around 66. That's good enough for our estimation. Okay, harder here. This is the second problem. So usually there's a total quantity equation, and then the second one's kind of either money or some sort of comparison between the two. Like a cost equation is usually what appears in a lot of other problems. There's no cost here, but there's a comparison equation, a comparison relationship that we can come up with here. Okay, it says here there are 4 times more Turks than Kurds living in Turkey. So the inclination here is to be, well, if we translate this, I might put 4t equal to k, And that's what a lot of people do. But you got to think, when you get problems like this, I quickly kind of do it in your head. Well, let's pretend here there are 4 times as many Turks than Kurds. So which one of these is going to have to get multiplied by 4 to equal the other one? Do we need to multiply the Kurds by 4 to equal the number of Turks? Or do we need to multiply the Turks by 4 to equal the number of the Kurds? Well, which one's bigger? Is Turks bigger or is Kurds bigger? Well, let's test some values in your head. What if there were, say, what if there were 2 Kurds, right? Just 2 Kurds living in Turkey. How many Turks would there be? Well, there are 4 times as many Turks as Kurds, okay? So there would be 8, right? There would be 8 Turks. So we'd have to take the 2, and what would we have to do to it? Oh, multiply it by 4 to get to 8 Turks, okay? What if there were 5 Kurds? How many Turks would there be? Well, there are 4 times as many. There would be 20 Turks. So what will we have to do to the Kurds to get to the Turks? We'd have to multiply by 4. So this here, the 4 would actually be in front of the Kurds. And that is a point of confusion when you set up those problems. You take the number of Kurds you have to multiply by 4, and that's going to be equivalent. It's going to equal the amount of Turks you have. To solve this one, you all know what to do. We have 1 equation, we have 2 equations. So now we've defined our variables, have our equations, so we're going to solve by substitution. So I got k, and because t is already isolated here, it equals 4k. I'm going to substitute 4k in for t and equal to 66. And this is nice too because we're trying to find out how many Kurds we have. So we just need to solve this. 5k equals 66. And I'm going to divide by 5. And I'm going to get 13.2. So my solution to this one here is about 13.2 million Kurds live in Turkey. All right, so that was a little review, it looks like, of solving a systems word problem. And I'm guessing they're doing this because, are we gonna have more words here? Does this look like another word problem? Okay, yes, this is another word problem. So my guess is that they're gonna have a linear inequality word problem that we're gonna have to solve right now. This was a linear equation. These are both linear equations here. This is equal to that, and this is equal to that. 2 variables and no exponents. My guess is that this will be a linear inequality that we're going to have to solve now. Okay, so let's check out this one. Ooh, we're staying with the whole country theme here. In 1912, Japan gave the United States several thousand flowering cherry trees as a symbol of friendship. Similarly, the nation of Cameroon plans to give flowering sada trees to other countries this year. When asked how to decide which sada trees make good gifts, Cameroon's chief arborist explained, well, we plant sada trees when they're 6 centimeters tall, and they grow 9 centimeters every year. The trees only flower when they're taller than 150 centimeters. So just looking at this here, you're putting on your hat, like your math hat. They've got some numbers right here. So we plant trees when they're 6 centimeters tall. What does that sound like? What type of a number does that sound like? We'll get back to that in a second. This one's easier to spot here. And they grow 9 centimeters every year. Ooh, we see that word every. So that's kind of like every or each or per. When we see that, every, each, or per, it's going to tell us kind of linear. It's growing linearly because it's growing consistently, but it's telling us, well, growth, right? Growth. What's that called in a linear function? Oh, that's right. That's the slope. Okay, so it looks like we have slope. It looks like this is going to be the starting, right? Because they plant trees when they're 6 centimeters tall. And then we have another piece of information. So it looks like we have enough for a linear equation or an inequality or something. And it says the trees only flower when they are taller than 150 centimeters. Okay, so that might help us come up with an inequality that you might be thinking of because, we need to look at the exact question that we have down below. It is very important that the trees Cameroon gives flowers this year. It would be considered an insult to receive a tree that did not bloom. Luckily, Cameroon has many groves of sada trees from which to select its gifts. How old must the trees be so that they will flower within the year? All right, so we had to discuss the team with our study team whether an inequality or equation is appropriate for this situation. Be prepared to share the reasoning. So the goal is how old those trees got to be so that they flower within the year. Well, when do they flower? So they flower when they're taller than 150 centimeters. They can't be really young because they're only 6 centimeters when they're born, and then they grow 9 centimeters every year. So let's think here. What kind of trees would be acceptable? Well, they have to be 150 centimeters tall, right? Oh, wait a second. They'd have to be at least, so greater than or equal to 150 centimeters tall. So I'm thinking inequalities here because it's okay. If we read the word problem here, if we're trying to figure out, is it okay just to be one particular value? If it's just one particular value, that's going to be an equation because that's one value equaling another value. If it's one value or values bigger than that or smaller than that, it's going to be an inequality, right? An inequality statement. So it can be equal to 150, but it's okay if it's greater than 150 centimeters. So I'm going to put inequality here. And here's my because statement. And I underline this. I say larger than 150 centimeters. So things like larger thans, bigger than, taller thans. When you see this word than, a lot of times it's going to be an inequality. Greater than, less than, taller than, larger than, smaller than. Things like that can be an inequality problem. Write and solve a mathematical sentence to determine how old the trees can be so that they flower each year. Let's try that trick. We got to write a math sentence, so we got to go to the end of the problem to help us figure out what our variables are going to be when we write the problem. So let's define that now. So it says how old the trees can be. And are we talking more than one tree? No, we're talking just the SATA trees here. So let's let S equal the number of years a SATA tree is, and that's going to determine how tall that tree is. So we don't need a second variable here because we're just trying to figure out how tall the trees can be so that they flower this year. And if we start with our starting number here, okay, so originally it's 6 centimeters tall, and then every year beyond that, it grows at 9 centimeters. So S is measured in years. So if S were 2 right here, this would be 9 times 2 would be 18 plus 6, it would be 24 centimeters tall. Is that greater than or equal to 150? No, that's not. So S would not be a solution. If S were 2, that would not be a solution to this inequality. But here's my inequality right here. I just finished it. Were you paying attention? Did you see what I did right there? You start with 6. You add 9 centimeters every year. So you're just kind of writing this out like a linear expression right here in y equals mx plus b form. So mx plus b, 9 centimeters every year. And I've defined S as the number of years. It's not a tree is, how old it is. And we add the 6 to it. We add 9 every year. It's got to be greater than or equal to 150 to satisfy the requirements of Cameroon here. So S needs to be a pretty big number. So if we're plugging some S's in our heads, is 10 going to be enough? Well, that would be 90 plus 6. No, you'd only need 96 centimeters if it's 10 years old. So it's got to be older than that. So my guess is in this next problem, or what? Actually, in this problem, we need to solve this inequality to get this thing done. We can figure out how old it is. So I'm going to write solve here, and let's go ahead and solve this. Again, first step, solve for boundary point. You know what that means at this point. You got to change this to an equation to figure out exactly how old the SATA tree needs to be a 150 centimeter tall tree. Subtract 6 from both sides. Again, start away from the S, right? Start simplifying away from the S. Reverse PEMDAS. Addition comes after multiplication in PEMDAS, right? A is the second to last letter in PEMDAS. So we do reverse PEMDAS when we're solving. So we get 9S equaling 144. And 9S goes into 144 16 times. That's one you'll do in your head a lot. 154 divided by 9 is 16. Okay, so we know that it needs to be 16 years to be exactly 150 meters. And we know because we're getting bigger each year, it's got to be, our final solution is greater than that. So S needs to be greater than or equal to 16. What you can do to be totally sure, right, is you can just test points, right? You can test points and get this done here, right? So test 0, for instance, right? That's really obvious. 0 would just have a 6 right there, right? You'd be a brand new plant. 0 times 9 is 0, and plus 6 is 6. 6 is not greater than or equal to 150. That doesn't work. So it needs to be the other side from 0 than 16 is. So values bigger than 16 for the years is going to give you a taller tree. So let's write that as a sentence for ourselves too. All right, part C to wrap this thing up. Later, the arborist added, I almost forgot to tell you, when the trees became very old, they stopped flowering. Make sure you choose trees that are no more than 240 centimeters tall. Ooh, so it looks like we have another inequality to consider here. So in this one, it needs to be at least 50 centimeters tall. And this one here, it can be no more than 240 centimeters tall. So it sounds like, here's what you're going to do is when you look at these the first times, figure out, is it okay if they're exactly 240 centimeters tall? Yes, it's totally okay. So what we see here, it says just no more than. The symbol for no more than is going to have an equality in here because it's okay if exactly, right? If it equals 240 centimeters. So it says here, discuss with your team how you can use this additional information to make sure you choose trees that will flower. Please prepare your answer with the class. So there are two options here to answer this final problem. We can come up with a brand new inequality showing that 9s plus 6 needs to be less than or equal to 240. But what I think this problem is getting at, because it's okay if it's exactly 240, but it can't be larger than 240, and so 240 needs to be the largest it can possibly be. I think what this question is getting at is actually writing something called a compound inequality. A compound inequality is two or more inequalities within the same math sentence. And I'm going to put this over here, and I'm hoping maybe you came up with this. But this would be a compound inequality. How would we read this? Well, we read inequalities the same way we read equations, which means left to right, which is the same way we read books, right, in the English language. So this is a compound inequality where we need to have a minimum height of 150 and we have a maximum height of 240. So the amount of years and the height that the trees will be when they flower is wedged between these two values. What these inequality symbols, there's another word for this that'll come up in future classworks. What these are called constraints. Constraints. We are constrained. You might have heard this. We're constrained by this in this situation, right? We're held down. We're constrained. We're held back. Constraints are something you'll study quite a bit if you do economics like I did in college, or you'll study these quite a bit in Algebra 2, something called linear programming. Sounds fancy, and it's pretty fun stuff. I like problems like that. Did it a lot in college. But constraints are two or more inequalities that are being applied to a situation, saying your situation's got to be between these two things or limited in some way. A constraint is basically a limitation of some sort. We're limited here where a tree needs to be at least 150, but it also needs to be less than 240. So this would be a way to represent this, and you can solve this. So we already know that S needs to be greater than 16 to be larger than 150 centimeters, but it would also need to be smaller than, well, I'd have to subtract 6 from both sides. I get 234, so then I divide by 9, and I get whatever S is there. It needs to be smaller than 20 something, right? I'm not really doing that in my head. I don't really feel the need to right now. 20 something years old in order to satisfy those constraints in that compound inequality. So a compound inequality is two more inequality symbols. Another thing we can call an inequality is constraints. So we have two constraints here. Lots of language coming at you in math, and but I think constraints is one that's easier to remember because it's something that you get constrained by. So constrain is actually the verb that goes with constraints. So when you hear constraints problems, you're thinking inequalities. We can only go up as high as this, right? Or we need to go higher than this because we have to. And it's okay if we go past something or below something, as long as we satisfy the constraints, it's okay. All right, there we go. More solving inequalities and solving an application word problem. Lesson 9.2.2. Again, happy Monday. Hopefully this went well. I will talk to you guys soon.